Hey, I want to give you a little introduction to this friend we like to call the psi function. Let's take a look. First of all, I want you to just consider this function. What is it doing? I'm talking about the function g of x. Notice the function g of x is defined as an integral function. Specifically, the integral of sine t over t dt from 0 to x. So just in your head right now, I'd like you to think about what is the purpose of g of x in this context. I don't mean like in the real world or what everyday application does this have. I'm not talking about that. Just from a purely mathematical perspective at this moment. As you look at this screen, as you look at this function, g of x serves what purpose? The purpose that g of x serves is its job, if I could give it a job. The job of g of x is to keep track of the accumulated area underneath the function sine t over t between 0 and whatever input x that I want. For instance, g at 0, when x is 0. The integral from 0 to 0. The accumulated area between 0 and 0. No area has been accumulated yet. So we would say that g of 0 equals 0. And then we could go on. What about x is 1 or x is pi or x is whatever? As x varies, x is the input quantity that varies. And as x varies, g of x is going to keep track of how much area has been accumulated underneath the graph of sine of t dt. So we should probably examine the graph of this function. I'll call it f of t just to keep things separate. F of t is the function sine of t over t, where g of x is the function that's keeping track of the area, the accumulated area underneath that curve between 0 and x. So we're just going to focus on the sine of t over t. So imagine like when t is 0, the sine of 0 over 0. Sine of 0 divided by 0 is like a 0 over 0 thing. So nothing's there. But then as the input quantity t increases, the sine of t over t is sometimes has positive, sometimes has negative, sometimes has positive, sometimes negative, because the sine function is sometimes positive and sometimes negative. So the sine of t over t is going to be sometimes positive, sometimes negative. And you might explore this function, just like imagine or actually get out a calculator and compute for different input values of t. What kind of output values do you get and why? Now, of course, what we're really going to focus on here is not just f of t in isolation, sine t over t, but this function g of x, whose job it is to keep track of the accumulated area underneath the curve. Imagine accumulating area from 0 to, maybe you can imagine this is pi, because the sine of pi is 0, and the sine of pi is 0 divided by pi would be 0. So imagine accumulating area little bit by little bit by little bit from 0 to pi, and then accumulating area from pi to 2 pi, etc., 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 etc. What would this function look like? Well, you've learned in this class that there's a very tight connection between accumulating area and the antiderivative. So one might be inclined to pursue the antiderivative in this case. So suppose you just are going to pause for a minute. We'll go back to g of x for just a moment, in a moment. But first, suppose you're just thinking, well, let's just find the antiderivative of sine t over t. Sometimes, when I've done this in the classroom, students will say, well, let's see, the antiderivative of sine t is negative cosine t, because the derivative of cosine is negative sine, so you have to counteract with the negative. The antiderivative of t, let's see, you increase the power by 1, and then you need a 1/2, so yeah, I think that would be it. No, you cannot just integrate the numerator denominator of this rational expression over here. And in fact, if you checked it, we'll just check that with Wolfram Alpha. The derivative of this should take you back to this. I don't have the time to do that in the video, so let's just have Wolfram do it for us. Is the derivative of negative cosine t over 1/2 t squared, is it just sine t over t? No, because to take the derivative of this, or in this case, this version of it up here, you would need a quotient rule. And a quotient rule is going to produce ultimately this, not just sine t over t. So no, that is not going to work. So then sometimes students, if you were in the classroom and I was bugging you about this, sometimes students would try integration by parts. They would think of this as 1 over t times sine t, u times dv, and they would go through the whole integration by parts business, and you can pause here and kind of see, but the point is this: u times v minus the integral of v du. The integral of v du is going to give you a cosine t times a 1 over t squared. Where we started with sine t times 1 over t, we now have cosine t times 1 over t squared. In fact, this integral in the integration by parts is getting worse. And if we just tried to keep going, it's not going to go. So then sometimes students try, well, let's just flip this thing around. Instead of 1 over t times sine t, let's think of it as sine t times 1 over t. And let's try integration by parts. Let's let u equal sine t and dv be 1 over t dt. So I'll let you pause and you can study the integration by parts here, but if we go u times v minus the integral of v du, now we have to integrate natural log of t times the cosine of t. Things are getting worse once again. So then somebody at some point, if you were in the classroom, is going to say, can we just use Wolfram Alpha? Hey, you saw the video on that, I hope, by now. And I would say, yes, it's 2020. Let's see what Wolfram Alpha has to say. And then as curious, intellectual human beings, we might pursue, why does Wolfram Alpha say that? Well, you see, the integral of sine t over t dt is psi of t. What? Psi of x is the sine integral. What is all that about? Well, here's the reality. There is no elementary function, as we say. There is no construction process you could engage in. There's no technique that you could engage in to produce an elementary function whose derivative is sine t over t. But since this integral is useful in different fields in engineering, and optics is a especially common place where this integral might be useful, we just give it a name. We call it the sine integral, the psi of t. So let's kind of examine this even some more using Desmos. So I'm only showing you the graphical side because I don't want you to be focused on my stuff that made Desmos do this. But here is that function sine t over t that we were examining earlier. And what we're interested in is the function whose job it is to keep track of the accumulated area underneath that curve. So to help you kind of visually to do just that, to keep track of the accumulated area under the curve, consider this, please. Accumulate some area. Accumulate some area. Accumulate some area. Do you see how in this first chunk we've accumulated area kind of quickly initially because of the height of those rectangles you could imagine in there? But then we accumulate area, but not as quickly because the rectangles are getting shorter. And then we accumulate area even more slowly out here. And so the function you might imagine right now is the function that's increasing concave down, increasing at a decreasing rate. But then we continue to accumulate area, but as you see there in purple, the area is below that horizontal axis. We call it negative, just assigned location, it's below, so negative area. So some of this positive area that we accumulated is now going to be taken away from, so we would expect to see some decreasing feature in this g of x function on this purple interval. But then we go back to positive area, we accumulate some positive, and then some negative, and then some positive, and then some negative, and you notice that the amount of positive followed by the negative, followed by the positive, followed by the negative. The amount of area that we're accumulating gets less and less and less. As we add some of that blue area, we take away less in purple, then add less than that in blue, and then take away less than that in purple. And so we would expect our function to kind of fluctuate, but not go back to zero, because we did start off with a good chunk of positive area, relatively speaking. So, you want to see it? Let me rewind so you can see it. Here is the function g of x visually. We accumulate positive area, but remember I said it would be concave down, because then we've accumulated all the positive area that we can, and now that negative area in purple is going to take away from the positive area we had accumulated. But then we're going to go back to the positive, so we'll have an increasing function, and then back to the negative, decreasing, and etc., etc., etc. We have this fluctuating function, but fluctuations become less and less and less dramatic as x increases. In fact, there's a limit that's reached here. In fact, there is a, let me show it to you. There is a limiting amount of area that is accumulated in this thing. Let me rewind it so you can see it. So accumulate, but then decrease, increase, decrease less, increase less, decrease less. This thing is getting closer and closer and closer as we add and subtract accumulated areas to pi over 2. Yeah, as x gets bigger and bigger and bigger, our function g of x gets closer and closer and closer to pi over 2. Now, I'm going to have to pause this video here because I'm making it too long. I'll break it up into another piece here. But so far, I want you to have in your brain, there's two functions at play. There's the function, what we're calling f of t, that blue function that's keeping track of just the sine of t over t function. Then there's the function we're calling g of x, which is keeping track of the accumulated area underneath that curve. So we saw that increase and that decrease, and the fluctuations get less and less dramatic, and this function seems to want to settle down around pi over 2. Now there's more to be said about this, but I'm going to pause there for now and let you ponder it.